for Di Girolamo. I got his last name right. I didn't get it right last month. And probably Christine Godfrey and Greg Bacon are looking on as well. So please give them a hand. All right. Are we all ready? Let's begin. Good evening, ladies and gentlemen, and welcome to the Hubble Space Telescope Public Lecture Series. It is my joy to be your host. I'm Dr. Frank Summers of the Office of Public Outreach. When you came in, there were lithographs on the tables over here and here. Tonight's lithograph is Messier 104, the Sombrero Galaxy. Really one of the really cool galaxies out there. If you look at the central region, it looks like an elliptical galaxy. If you look at the outer regions, you see a disk like a spiral galaxy. This is sort of an S0 lenticular galaxy. It's a really cool galaxy. You want to know more about it, you can look on the back and read all about it. If you didn't get it on the way in, please grab one on the way out. Our speaker tonight, the composition of galaxies looking beyond the stars, looking beyond those stars that you see in that lithograph, Lauren Corlies from Johns Hopkins. Very glad to have her here tonight. Next month, David Law will be talking about integrated field unit spectroscopy, and I know that sounds ever so geeky. Oh my God, it's really not. It's a developing field that's gonna really change the way we do a lot of science, okay? Integrated field units. I asked him if he wanted a more exciting title, and he didn't quite come up with one yet. Maybe he will before next month. In May, Mia Bova will be coming back. She spoke last year on the Harvard computers, and note that's in quotes because this is the team of women who worked at Harvard Observatory on the classification of stars and the development of the HR diagram. An incredible story. If you know it, you'll certainly want to hear it again. June 27th, we are having a special WFIRST workshop in association with WFIRST. WFIRST is the Wide Field Infrared Space Telescope that will be launched in the mid-2020s. We're doing a WFIRST workshop, and we got Amber Strawn from NASA Goddard Space Flight Center to come up and give a talk on astronomy in the 2020s, synergies with WFIRST, how Hubble, if it's still working, and JWST, which will be working, and WFIRST will all work together to create science that, just amazing swaths of science by working together. This is the great thing about having NASA having several great observatories, is that we really get to use the observations from one to complement the other, and we really get multi-wavelength views of these objects and learn so much more. Our website for the upcoming lectures, if you just go, we have the Go link up here, but if you just go to your favorite search engine and put in Hubble Public Talks, you will get this. You have a list of the upcoming lectures, the link to the webcast, the archive of the webcast going back to 2005. So that's 12 years now. We're approaching 12 years of webcasts on there. That'll keep you busy for, if you want to talk about binge watching, okay, that will keep you busy, okay? You can also stay informed by adding your email address to our mailing list. We have these announcements. You can sign up at the website, or we have an alternative one for mail list at stsci.edu. If you would like to send us email, you can send it to publiclecture@stsci.edu, and I and my colleagues will read it and answer it for you. Social media, we're on Facebook. We've got 2 Twitter feeds. We're on Google Plus and Pinterest. I myself do every now and then do a blog on Hubble site. I'm a little bit on Facebook, Google Plus, and Twitter, but as I like to say, I have lots of important things to do, so I am not on social media as much as some other people are. Let's see, the observatory, always weather permitting. Did you guys get rained on when you came in? Yeah, weather's not permitting, sorry. So if you would like, I do believe they run open houses on every Friday. Go to md.spacegrant.org and you can find out their schedule for when you can look through the telescope. It's actually, we were talking about it before, that it's been several months since we've had a clear Tuesday, first Tuesday. Hopefully next month. All right. So now my part, news from the universe for March 2017. Our top story, everybody knows what it's going to be. Red Dwarf and the 7 planets. So, I went to exoplanets.org yesterday, and I checked how many planets we have detected outside of our solar system. We have 2,950 confirmed planets out there. Plus, there's some unconfirmed candidates for over almost 5,500 potential planets out there. So, who cares about another 7? Okay, we added 7 more. Ooh, exciting. Is that really news? Well, yes, because this is 7 planets in one system. This is the TRAPPIST-1 system. And TRAPPIST is this long, involved acronym that I'm not going to try and remember. But basically, we're looking at a star and detecting the planets passing in front of that star and the light of the star decreasing just a little bit. Okay, and that's what the TRAPPIST project has been doing. And the TRAPPIST-1 system, the Spitzer Space Telescope did follow-up observations on it and got confirmation of 1, 2, 3, 4, 5, 6, 7 planets around it. Now, what makes it cool is that the colors here indicate the habitable zone. Basically, the zone in which liquid water could exist on an Earth-sized planet. So the green is the habitable zone. And what do we get? We get 3 planets directly in the habitable zone around this star. All right? So for TRAPPIST-1, we have 7 planets. All of them are Earth-sized. This is the largest number of Earth-sized planets in a single system. We have 3 planets in the habitable zone. This is the largest number of Earth-sized planets in the habitable zone for any system. And what I think is actually most important is it orbits a red dwarf star. Not just any red dwarf star, a tiny red dwarf star with 8% the mass of the sun. Okay? This red dwarf star is only 85 times the mass of Jupiter. Right? We theorize that you probably need about 70 times the mass of Jupiter in order to become a star. So this is just above the stellar cutoff. If the smallest stars in the universe can have this many planets, and the smallest stars are the most abundant stars in the universe, we got a lot of planets out there. And that, to me, is what's really exciting about this, okay? The other thing to know about this is that because it's a small red dwarf star, these planets are in really close. How close? All of these planets, all 7 of these planets are in here, and this is the orbit of Mercury. Okay? They are well inside the orbit of Mercury. Okay? They are down to less than 6% of the Earth-Sun distance. That's tiny. Okay? Compact in there. So it shows you that in these red dwarf planetary systems, the planets have to be huddled up close to the fire to stay warm, right? In order for this, all right? Now, these, however, are not what we see. These are artist depictions, okay? They're artist drawings of what they could possibly look like. Do we know what they look like? Absolutely not. What did we actually see? I like to show you the real data, okay? So this is the data of what we saw. And here it is, right there. This is what we saw. Now, what you're seeing is the light curve, okay? So this is the light of the star. And you see these dips here? These drop downs? This is when a planet passes in front of the star and the light of the star decreases by a little bit. You'll notice that this is 98%. So the total drop here would be 2%. Okay, that's the maximum drop is like a couple percent. All right, so we're seeing these 1% drops in the light, and from them detecting that there are planets there. Why? Because they are periodic. So look at B, 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 B. You see these periodic dips as the planet passes around. Every time it orbits, it passes in front. Okay, and then you've got the same for C, D, E, F, and G, and H. Although I noticed in the data that they released, there's only one H. So that's kind of hard to say. I'm sure they have much more to indicate the long term of age, but the data that they release. So this is how we actually see them. We just see the drop in the light to detect the planet passing in front of. We see that it's periodic, and that gives us confidence that these are planets passing in front of a star. So this is a really cool system that you probably heard a lot about. My mom actually started asking me about it, so I know it has to have made a lot of press when my mom is asking me about it. Okay, the star is only 40 light years away. It is, I said, it's a mass about 8th out of the sun, but its diameter is only 10% larger than that of Jupiter. Here's a drawing. That's the size of Jupiter. This is the size of the TRAPPIST-1 star. You add 85 times the mass of Jupiter, but it only grows by about 10% in diameter. That's the sort of thing that happens as you go from large planets to small stars. The planet sizes, they're all around Earth size, from 3/4 to just over 1. The mass estimates based on some density ideas go from about 40% to 1.4 times Earth, so these are Earth-sized. Okay, so they're not only Earth diameter, they're also Earth mass, which gives us great hope that they will be rocky and not gaseous. I mean, one thing is that they could be Earth-sized, but they could be mini Neptunes instead of being Earth-like, right? So we know that they're Earth-sized. We do not know that they're Earth-like. And as I said, the orbits are tiny, from 1% to 6% that of Earth. The period are 1.5 to 20 days, okay? Orbiting around the planet, or the planet orbiting around the star once every week, up to 3 weeks maximum. It means that these planets are likely to be tidally locked. There is no dark side of the moon. Every part of the moon gets light, but on these planets, they are tidally locked to their star, so they do have a dark side. They would have a side that's permanently in light and a side that's permanently in dark. All right. The other cool thing is if you could imagine sitting on one of those planets and seeing the other planets in the sky, they'd be big. From one planet to another, it could be as big as 3 times the size of the full moon. All right, so this is a cool imagination of a wonderful system, and shows you that we have an amazing number of discoveries out there possible when we're looking at extrasolar planetary systems. Yes, question?
Orbits like that.
So this is a question I don't have a good answer for, but let me repeat the question for the online audience. So when you form a solar system, you actually form lots of planetesimals up to the moon-sized and start to build up towards Earth size. And when they gravitationally interact, they can become unstable and kick planets all over, then can crash in. So the question is, how do you get 7 planets in such a tight configuration and keep it stable? I don't know. We just discovered this, and I haven't I haven't seen any analysis to see what the stability of the system is. Are there resonances in these orbits? If you look at the orbits of the moons of Jupiter, there are resonances between the first, the second, and the third of the Galilean moons, and those resonances make the orbit stable. I don't know if this star is billions of years old. Has this system been around for a billion years? I don't know enough details of the star to say that. So there's, yeah, you are right. That's an interesting question, and I'm sure somebody out there knows the answer already, just not me right now. Okay. Yeah.
You just answered it. They don't know the age of the star.
I don't know the age of the star. Maybe somebody else does, but it's hard to measure ages, especially. Well, they can measure ages for these small stars by looking at the lines of the volatile elements in the atmosphere, the elements that disappear over time. But I do not know that they've done that yet. Yeah.
My question is about the tidally locked. Does that is there a limitation on the rotation of a planet that just can't rotate so fast that it could rotate around the star also?
Right. So the point is that when two bodies are close enough together, gravity will produce a tidal locking because there'll be inhomogeneities in the internal structure. So it'll wobble, it'll slow down the rotation until one side always faces it. Earth and the moon, right now the moon always has the same side facing Earth, right? In about, I don't know, a few 100 million years, Earth will always have the same side facing the moon, okay, as Earth and Moon settle into a system where they're tidally locked. Pluto and Charon are tidally locked. They always have the same side facing. So in that same process is believed to probably be in effect here, where all 7 of these planets are tidally locked to their star. They're close enough in for that to happen. All right, last question, then I have to move on because I don't want to delay Lauren's talk too much.
Are there any other planets in the system besides these 7?
Any other planets in the system besides 7? Not that we have detected. Okay. It actually originally the TRAPPIST folks detected 2 planets, the inner 2 planets, and it's the Spitzer follow-up that detected 7. Maybe there are more. Complex signals take a while to be deconvolved, but they will continue to look to study the system to see what they can find. Okay. All right. Let me move on to my second story. And my second story is the 30th anniversary of supernova 1987A. How many people remember in 1987 when we saw this? Okay, not that many. Okay, where was I? I was in college back then. I was in college, and I actually thought a friend of mine was joking and saying, "Oh, we saw a supernova," because you never see a supernova. It's been 400 years since the invention of the telescope, and we haven't seen a supernova nearby until 1987. So this is a field of stars, and on February 23rd, 1987, boom, okay, we had a star explode as a supernova, all right? And as I said, we haven't had a nearby one. This one is nearby, but not quite so nearby. It's actually in the Large Magellanic Cloud, so it's about 170,000 light years away. All right, we should get one supernova every 100 years in our own galaxy. We haven't seen one since 1600s. It's a real pain. All right, it turned out it was a blue supergiant that exploded, which at the time we didn't think blue supergiants could go supernova. We have since been corrected by nature itself, and then adjusted our scientific understanding to go, yeah, all right, now we can see how blue supergiants can explode. And it was the first supernova for which neutrinos were observed. We have these neutrino detectors looking for the neutrinos from the sun. They actually detected like 9 neutrinos from this supernova. They detected them a couple hours before the star brightened. Okay, that's just the way the physics of it works out, of the supernova works out. The neutrinos were released before the light is actually released, and so they're saying. However, a star of this size should collapse to form a neutron star, and for 30 years we've been looking for that neutron star, and we still haven't found it. So something else funky is going on there. There is a neutron star that we're looking for. All right? So let's talk about where it is. It's in the Large Magellanic Cloud. Here is a visualization to show you just how small and tiny it is on the sky. That's the Tarantula Nebula above. So we're below the Tarantula Nebula in the Large Magellanic Cloud. And we keep going in and keep going in. Yeah, you'd never find this star unless it exploded. And that is what supernova 1987A looks to like today with the Hubble Space Telescope. So, actually, this should say 2017. I thought this was the June 2016 image. It's actually the January 2017 image. I'm wrong on that. But you can see that here is where the supernova occurred. All right, this ring here and these other 2 rings were pre-existing. They were out there. Actually, I'm going to show you. This is what Hubble saw in 2017, and this is what Hubble saw in 1994. I'm going to use the 1994 image to show you the details. Okay, so this is the position where the supernova occurred. Okay, these are foreground stars. Don't let them confuse you. They're not brightening. They're not associated with the supernova. These outer rings are somewhat of a mystery. They were obviously released before the supernova. They were illuminated by they are ionized by the flash of the supernova. And they appeared a few months after the supernova. How they formed before that, we're not sure. Okay, we had a couple ideas, and then those turned out to not be so right. But that's science, you know. You take your best guess, and then if it's wrong, you go back and do another one. This inner ring, however, is the really cool thing. Okay, this is a radial ring that's about 1 light year across, 1.3 light years across. Okay, and we've watched the development of that from 1994 to 2016, and that's shown in this movie. So you can see the ring starts out relatively, and then it starts to lighten up as the blast wave hits it, and all of the dense regions in the ring become illuminated over the years. Okay, this is the blast wave from the supernova spreading out and hitting the ring, which I can use my hands to show you this, but it's so much easier if I happen to have a supercomputer simulation running adaptive mesh refinement at an effective resolution of 2048 cubed. Oh, I do happen to have one of those. It's on my next slide. So this is a simulation from a gentleman in Italy, and he shared the data with me, and I was able to visualize it to show you the blast wave running across the ring. So here is the Sandeliac star, and here is the ring, okay, and here is the simulation. That's the supernova. And you can see the blast wave moving out and hitting the ring. And as it hits the ring, the dense clumps in the ring are heated and ionized. And if we rotate around, you can see the structure of that ring. And that's the 30-year history of supernova 1987A. So, whoops. So this is what this supernova looks like after 30 years. And it's been really cool being able to watch something develop for 30 years. And what's even cooler is to think about what will look like 1,000 years later. Because on the left, I'm showing you the Crab supernova remnant. And Chinese astronomers observed the Crab supernova explode on July 4th, 1054, almost 1,000 years ago. So this is a 30-year-old supernova remnant. You can see that stuff in here. And this is a 1,000-year-old supernova remnant. And it will be cool for astronomy to be able to watch this and see that supernova. They grow up so fast. All right. That's our news from the universe for tonight. And now I am going to very pleased to move on to our featured speaker. Lauren Corlies is your postdoc over at Johns Hopkins University. She's working with Molly Peoples, and she's going to describe, I would say what she's been doing, but she's going to describe it tonight for you. And it's been, I don't know, several months we've been trying to get you to organize on this. So I'm very pleased to have her. Ladies and gentlemen, Lauren Corlies.
Thanks for being here despite the bad weather. I'm impressed by the turnout. And also pretty excited because, as Frank mentioned, this is the first time I'm talking to a public audience about the thing that I do every single day. And since it's what I do every day, I thought I'd start with how I got interested in this topic when there's so many cool things to talk about in astronomy. So I did my PhD at Columbia University up in New York City. And the program there starts out so where you can do a first year and a second year project. So you get to try out a bunch of different stuff, and you also get to try out different thesis advisors before you have to pick the one thing you're going to work on for the foreseeable future. And they shop around. They try and convince you to work on projects. And the one I wound up picking was on galaxy simulations. And in particular, it was connecting simulations to actual data that we have, which is my favorite thing to do. But I went to my first meeting with my new advisor trying to be impressive, and she starts talking to me about this galaxy that we're going to simulate, and I realized that I have absolutely no idea what she's talking about, which was surprising because, you know, I thought I knew what a galaxy was, right? Like, this is a galaxy, everyone knows that. I particularly like this galaxy because it's a really great example of the beautiful spiral structure that you can see in the universe. So this is the Whirlpool galaxy. And again, when I think of galaxy, especially at that time, this is what I was thinking of, the spiral arms. You could see all of the stars, especially in the center, that extend out. This one actually has a companion, which is pretty cool, that we think is driving this tidal or this spiral structure that you're seeing. So galaxy, right? And funny enough, I also picked this image. If you turn and look on the edge on, you can see, okay, yeah, there's stars in the galaxy, but there's also, you know, this gas and this dust forming a thin disk. So, okay, so galaxies have stars and gas and a disk. I was pretty aware of the fact that there were elliptical galaxies. So instead of having disk of stars, they form this ellipsoid structure. And I should say, when I was sort of aware, I was a physics major, and so I went into astronomy without having ever learned anything about galaxies. This was pretty much all that I knew. And so my advisor was like, nope, none of that is right. That's not exactly what a galaxy is. Like, I'm going to draw you a diagram on the board, and sent me home with an introductory physics or Galaxies textbook, which was maybe not a great start, but we wound up doing my thesis together, so it worked out all right. So what exactly makes up a galaxy? So this is roughly what she drew on the board for me that day. So obviously you always want to start with the disk. So someone asked earlier about the idea of a dark galaxy. The way we define galaxies is that they're always going to have stars. So you can have a disk or an ellipsoid. But what they also sit inside is a huge dark matter halo, we call it. So as Frank mentioned, the universe is mostly made up, the matter inside of it is mostly dark matter. So we know it's there because of the effect of its gravity has on stuff that we can see, which are the baryons, which are in the disk. But we think that it actually dominates the universe. So what's happening is that you're going to have a region where there's more dark matter than in other regions. And the baryons, the light stuff, follow the dark matter, and they go into the center, and they're going to form the stars that we see. But what else is inside the galaxy is not just stars, but there's actually a huge amount of gas that extends all the way out past the disk as far as the dark matter does. Because as I just mentioned, if the gas and the baryons are following the dark matter, then naturally, wherever you have dark matter, you're going to have gas. So why don't we see this when we take the beautiful pictures of galaxies, is that this gas is very diffuse. There's not a lot of it in a single given space. But I've sort of drawn this in an inaccurate way. If you actually try to make this to scale, this is now where all of the stars are for the most part. There are stars in a halo around the main disk, but most of the stars reside in the disk, whereas the dark matter and the gas that's with it extends out 10 times further, or further than that. So if the disk is 15 kiloparsecs across, this dark matter halo is 300. So just by the nature of it filling up so much volume, even though there's not a lot of stuff in any given space, you're going to have a ton of stuff. So actually, most of the mass of the baryons in the galaxy is actually dominated by this gas outside of the disk and not the disk itself. So understanding it's pretty important, but we're used to thinking of stars because that's what we can see historically. I also find this gas very interesting because it's really complex. So the way I drew it, there was some structure to it, but it's even more complicated than that, and complicated makes it fun. So again, you can sort of see the disk here in the center, where all the stars are, but all around here is all the things that are going into making this disk able to exist at all. So we think that if stars are continuously forming, then the disk needs to continuously be getting gas in order to be able to form those stars. So that gas is coming from somewhere, and it must be from the space around the stars. So this area, on all this gas, which we refer to as the circumgalactic medium, it's around the galaxy, it must be feeding star formation. So if you want to form a galaxy, you have to understand this gas. The other thing that's really cool about this region is that the stars, when they die, go supernova, like we just saw. And those are huge amounts of energy that they deposit, that they give to the gas near them, that then gets really kicked out of the galaxy. So you can drive these huge outflows out from the disks, again, into this volume, which is quickly becoming incredibly chaotic since you have all of these different things happening. And then on top of that, the gas that gets kicked out doesn't necessarily go away forever. So we refer to this as gas recycling because the gas gets kicked out, falls back down to the disk, and can reform stars. So pretty much if you want to understand how anything is happening in the disk of the galaxy, you have to understand this gas around it. And I find that really exciting. The other thing to keep in mind is that this galaxy that we're talking about is one galaxy in a huge cosmic web, where every intersection point is going to be a galaxy. So if you want to understand how our one specific galaxy fits into this large context, you have to understand the outskirts because that's what's connecting to the rest of the universe. So understanding the disk of the galaxy and also understanding the galaxy's place in the universe is all connected to this circumgalactic medium. So this is just a video because if you're talking about simulations, you have to show a video. And this is by the Illustrious project, which I encourage you to Google because they've created a lot of really great images like this. But what you're seeing is time since the Big Bang. Right now it's in dark matter, and it's going to shift to temperature, which is going to trace the baryons, the stars and the light instead. And so what you see here is that there's a large amount of structure, and everything is evolving with time. So the colors correspond, like I said, to temperature. So you have clumps that are cold. You have these huge outbursts going off that are driving large amounts of gas to really high temperatures and to far distances outside of their galaxy. And you can see that they're all sort of connected together. So maybe some of this gas is falling in to form new stars. So it's a really complicated moving picture that's all evolving with time that leads into what we know as galaxies today. It's an especially interesting time to start asking questions about what all of these processes are, because we're finally starting to do some other things right. So historically, galaxy simulations have had a really hard time matching galaxy properties. So all the physics that goes in we think is what's happening, but instead of forming realistic looking galaxies, we form galaxies where all the stars are really concentrated in the center, and you don't really get spiral disk structures, which we know have to exist. But we're finally getting closer to solving that problem. So this is an image of the Hubble Ultra Deep Field, which is where what they've done is they've taken the Hubble Space Telescope, I don't know if everyone knows already, but they've stared at a patch of the sky for a really long time, and so you see the distribution of galaxies pretty much throughout the history of the universe. So the oldest galaxies that we know are in this picture. And I'm being a little bit deceitful when I call this the Hubble Ultra Deep Field, because actually, this half is the Hubble Ultra Deep Field, and this half is if you take that simulation that I just showed you and observed it as if you had looked through Hubble. And so you can see that we're starting to get actually really close to what the population of galaxies really looks like, which I always find this absolutely stunning because this picture couldn't have existed until recently. And again, like I said, these are actual simulated galaxies. These are no longer observations. So we're getting to the point where we're now thinking we're doing everything okay with disks of galaxies. But it's interesting to point out is that this is not an accident. We have very good measurements of what galaxies look like, what the distribution of galaxies are looking like. And so we take the simulations and we want them to match this information. So that's another reason why all of the gas that I was talking about I find particularly interesting, because that's not something that we've tried to get the simulations to match before. So if you can match the stars and then you just happen to also match the gas around them, then that's a really great confirmation of your theory. And if it's not, then that means that even though you're getting the stars correct in your galaxies, you're still not doing it exactly right because you're not matching the rest of the volume of the galaxy. So it's a new, exciting, independent test of what galaxy formation is like. So some of the questions that you can ask then is, how do we observe this circumgalactic medium? If it's so exciting, why haven't we done it before? What have we learned from the observations that we have done? And what challenges are ahead now that we have our first look at some new data? The first thing to point out is one of the reasons why this is so hard is that the gas is giving off light in the ultraviolet. So it's much easier to observe in the optical, especially from the Earth, because optical light actually reaches the Earth, as opposed to UV. So this is showing how light gets to the surface of the Earth. So you can see visible light is fine. As soon as you start going up into the ultraviolet, you're totally destroyed. So all of these observations have to happen in space. And there are two main methods to try and observe this gas. So the gas in the galaxy, in the outskirts of the galaxy, gives off light itself. It's moving, it's hot, so it emits light. So that would be great, just to see the light itself. An alternative method is if you have some light behind the galaxy that passes through it, and if we're over here, we can observe the changes to this light that were affected because of the galaxy. And by observing changes, you can know something about the gas that the light passed through. So that's a lot more indirect. So in terms of emission, ideally what we would like to do is say, okay, well, here's the center of the galaxy, we think. Let's measure how bright the gas is out to roughly the edge of it. And so you would get some sort of curve where you'd say, okay, it's definitely going to be brightest in the center, because that's where most of the gas is. And as you move out in radius, this will probably drop because there is less stuff out on the outskirts here than there is in the center. So it would be amazing to make this plot. But unfortunately, the brightness level that we can detect to is actually about right here. So all of this light that we're expecting to see from this circumgalactic medium is below what we're capable of detecting right now. So what we need to do is work on instrumentation to be able to take this brightness limit and move it down. So if you can move it all the way here, you could just observe all of the light from this galaxy. But unfortunately, we're nowhere close to that yet, but we're working on it. And I'll talk a little bit about that at the end. Absorption, on the other hand, is a lot easier because you're starting off with something that's incredibly bright. So if you have a really bright background source, and in almost every case this is a quasar, so you have a black hole that's accreting gas that gives off a ton of light because of that accretion process, and you can see them out to extremely large distances. So if you have a quasar behind your galaxy that you're interested in, the light from the quasar is going to pass through the galaxy, and then you can observe it with Hubble or your telescope of choice. The bad thing about this is that you're going to have one quasar, and it's so far away that it's essentially a single point. So you're measuring the gas of this galaxy at one point, and that's it. So if this point is radically different than this point, you'll have no way of knowing. To try and get around that, what we can do is say, okay, well, I won't just look at one galaxy then. I'm going to look at a lot of galaxies. I'll get points in a few of them. Some of them do have more than one. And you can plot their absorption as a function of radius, and you can get some sort of trend for this population of galaxies. Right now, this is the main way that we study this gas. And it's like I said, because these sources are so bright, you can actually measure this absorption to very low levels. So you can actually start to probe this gas that is there, even though there's not that much of it within a single line of sight. So the exciting data that I've been working with primarily is from a survey that was actually led here called COS Halos. COS refers to the Cosmic Origin Spectrograph, which is on Hubble, which is why I keep putting it in the corner. This survey was particularly exciting because the way we've done these kinds of studies in the past is you just look for all the quasars you can find. So for example here, you take a measurement of them. So this is the wavelength of light, and this is the amount of light at each wavelength. And you can see your quasar. And then this is a whole dark art. So as I mentioned, I work more on simulations, and so I'm just always amazed when people take this, and if you zoom in, you see these absorption levels, and they measure these with extremely high accuracy. It's a real talent. So what they're measuring is they say, okay, if there was no galaxy in the way, we think that this would be flat. And the fact that we see this dip here means that gas in the galaxy absorbed this light. And so they can estimate how much gas would be needed to cause that absorption, and they say, oh, there was that much gas within that line of sight towards the galaxy. This survey was particularly exciting because instead of just looking for all of these quasars, what they did instead was they said, okay, well, let's look for galaxies. Ultimately, that's what we're interested in. We don't care just finding this gas. We want to be able to say this gas came from this kind of galaxy. So they went and they constructed a population of galaxies that were all roughly the same mass as the Milky Way. We were interested in understanding what Milky Way galaxies looked like. They're all relatively nearby, so this is why we had to use COS. This is all done in the UV. You could look at galaxies that are further away in the optical, but like I pointed out in the movie, all of this is really evolving with time. So if you want to have some sort of sense of what galaxies look like right now, you have to look in the UV. And they looked for quasars that were or galaxies that were at a distribution of radii away from a quasar. So this is showing all of the quasars that they observed and the distances to the galaxies. So if this galaxy was 150 kiloparsecs, say, away from its quasar. And here you can see an image of what that would look like. So this one happened to have two galaxies nearby, and they've identified the absorption from these two galaxies. So in the sample, there was roughly 40 galaxies. So we have it's not an enormous population. It's not hundreds of thousands of galaxies like you talk about something with SDSS, but 40 is still quite a good number to be able to do science with. So what did they find? The first thing that they found was that galaxies have a lot of gas beyond their disks, which we had sort of guessed from the simulations that it should be there. That's why we did the survey. But even thinking that there was going to be a lot of gas out there, we were surprised by how much gas there is out there. So this is showing the radius from the center of the galaxy, and then this is the amount of neutral hydrogen. So neutral hydrogen is interesting because it's cold, and cold neutral hydrogen is what leads to star formation. So if a galaxy has a lot of cold neutral hydrogen, we expect it to be forming stars. And what was exciting about what we found was that so these points are color-coded by if the galaxy is forming stars or not. So if they're blue, they're forming stars, and if they're red, they're not forming stars. And what's surprising is that red galaxies that aren't forming stars actually have as much neutral hydrogen as galaxies that are in the outskirts of their halos. So the question then is, well, why do they have so much H1 and they're not forming stars? So that's something that we weren't expecting to find and is now something we have to incorporate into the simulations that we're running. And this was true of pretty much all of the ions that we looked at. There was just a lot of gas out there, especially at low temperatures that we weren't expecting. So it was really exciting. And to give you a sense of how you could relate this to a theory, to a simulation, what I've done is I've just picked 3 of these points that happen to not overlap in radius. So this is a simulation of the galaxy that I looked at the most. And this is also showing the neutral hydrogen within the simulated galaxy. The colors of these rings correspond to the amount that would be there at the point from the data. So anywhere that the color of the ring matches the color in the galaxy map is where the galaxy and the observation agree. So for example, for this ring, right around here is where the H1, the neutral hydrogen that's in the simulated galaxy, matches what's in the data. So you could say, okay, well, maybe in the data, what we're seeing is some sort of stream that seems to be feeding the disk of the galaxy. So you can start to try and make connections like this between the simulations and the data itself. The amount and type of gas varies with galaxy type. So this is the plot that I was showing before. So this is, again, the radius, and this is the neutral hydrogen. Here's the same radius scale, but what it's showing over here is oxygen 6. So oxygen 6 is oxygen atoms that have had 5 electrons removed. So to remove 5 electrons from an oxygen atom takes a lot of energy. And so this ion happens to trace gas that's a lot hotter. So this is something at around like 1,000,000 Kelvin, where this gas is more at 10,000 Kelvin. And what you're finding is that there's still a lot of this oxygen 6 gas, but that you do see now differences in the populations of galaxies. So these star-forming ones have a lot of this oxygen 6, and these passive ones, non-star-forming ones, don't. So that's also now something that simulations are going to have to be able to explain. And as I'm sort of hinting at, none of the simulations can match this data, which was pretty concerning if you do these kinds of studies, or pretty exciting when you're someone new like me, because that means there's a lot more new things to work on. So as I pointed out, these colors you need to match to the background galaxies. Ideally, what you would say is that we just did this survey blind. So we had no expectation that we were probing some sort of special structure in any of these galaxies. We just looked for any galaxy that was close to a quasar and observed it. So really, what these colors should be corresponding to is a large fraction of this volume. There's no reason why we should have identified this one specific feature that happens to be really strong. Especially, remember when you look at the distribution, it's not like I picked out this point that has a large amount of H1. It's just an average point in this trend. So it should correspond to an average, to an average point in this map, and it doesn't. Instead, we don't see nearly enough neutral hydrogen in the simulation. I should mention that the simulation is particularly bad in terms of this. Some of them do slightly better, but none of them actually match all of the data. So again, what's cool about this is that you haven't just measured one ion, you've measured a whole series of them. So you can ask, okay, it doesn't match in 10 to the 1,000 Kelvin degree gas, but does it match in hotter gas? Does it match in other ions? And the answer is it doesn't match in any of them, which again was pretty sad or exciting. It depends on if you're a pessimist or an optimist. So these are 3 different ions now that correspond to different temperatures. So again, oxygen 6 is the hottest, this one's the coolest, and this one's sort of in between the 2 of them. So this is just more of a quantitative way of looking at the previous slide. So what I've done is I've taken every cell in this projection, and I've plotted it here as the gray points, and then these actual data points correspond to the data that's in the previous plot. So again, ideally, you'd want the majority of your simulated points to match the data, and they don't. So to match any sort of the observations that we see, we'd have to always be probing special structures, which just seems unlikely. And what's especially concerning is that these data points have very good error bars, and we don't even match them at all. So this is hinting that there's something very wrong with the temperature distribution of our gas. And as I mentioned, this simulation does particularly bad, especially in these ions. Other simulations do better here, but none of them that I know of really match this one. So again, there's something fundamentally wrong with the theories of what the prescriptions that we're putting into our galaxy simulations, where we're matching the stars, but we're not matching the gas. And part of the reason that could be is that gas is constantly moving in galaxies, like I showed in the simulation, which means all of this is very complicated. And trying to match all of these individual processes is going to be something that's going to take some time to understand. And the fact that the data exists now is exciting, so we can begin to place constraints on what we're thinking instead of just having nowhere to go and searching blindly. So where do we go from here? What else is there? So in the simulations, one of the things that I'm particularly excited about is the resolution issue. So these simulations are incredibly complicated. So they're starting from that very large scale structure that I showed in one of the slides. And you have to zoom in all the way down to this level. You can't even see it. So the galaxy is under here. And what this is showing is how we decide to break up that computation. So you're going to be interested normally in this kind of simulation in one specific galaxy. So you identify it and say, that's where I want to put all of my computing power. And if you see, it's covered really well, especially in the center part of the disk where a lot of the gas is. The outskirts, however, you can see all these boxes are bigger. So we're not really refining these boxes as well as we are the center of the disk. And as you move out, this gets more and more true because you're less concerned about the larger environment of this galaxy. But all the observations that we're making are out here. So this goes out to 150 kiloparsecs, which is where the last data point was. So you're not sampling in here by design, you're sampling out here where all of the resolution isn't very good. So if the absorption, what we're measuring in the data, is being caused by anything that's smaller than this scale, we're not going to see it in the simulation. So maybe there's something that we're doing wrong here that we could be doing better. The other thing that I don't have a plot of is that, going back to this picture, all of these things, especially the outflows that are driven by stars, are prescriptions in the simulation. So we decide when and how the stars are going to form and when and how the stars are going to die. And again, that's something we've tuned to reproduce stellar properties of the galaxies, but clearly aren't reproducing these properties. And so people are working now to change those models. So the supernova, you can say maybe they give off more energy, maybe they give off the energy at a different time, maybe they give off the energy in a different distribution. You can also try and put in new physics. For example, a lot of these simulations we know do a really poor job of measuring any sort of energy from a black hole that's accreting gas. Maybe that's what's going to change all of the measurements that we're making in the simulations. So it's also an exciting time to try and figure out what else could be happening in the galaxy that we're now able to detect in the data. The other thing we could do is actually maybe just try searching an emission. So this, again, is exciting is because you're getting a whole map of a single galaxy. So you can say definitively for this galaxy, for example, that the oxygen-6 ion that you're seeing has this distribution. There's no questioning of, well, if I'm measuring this one point, does that correspond to a special feature? Is it something that's just generic in the galaxies? And this is work that I did for an instrument where we're trying to place probabilities on what our chances are of actually detecting this emission. So this is where I've taken the simulation and said, okay, this is how much light I expect to come from oxygen-6 from that galaxy. And it's color-coded by the probability of if we think we're going to detect it or not. So green means, like, yes, we're definitely going to be able to see that. And unfortunately, you'll notice that all of the green points are within the disk of the galaxy for the most part, which we already know is there, so that's fine, but not particularly exciting. What's better is that these blue points are things that we'll probably detect. That's what we're designing the instrument to be able to see. And particularly for some of these ions tracing colder gas, they extend out quite far. So if you see emission, you'll know the galaxy is here from looking for the stars. And if you see light from the gas that's out here, you're definitely going to be able to say, oh, I'm seeing gas associated with this outer part of the galaxy that I haven't seen before. And you won't be confused by saying, well, is this part of the disk or not? You'll be able to say for sure. And obviously what would be most exciting is if we could push the surface brightness limits down as far as possible, because then you could see even further. So you could actually be able to see a fairly good portion of the image of the galaxy. And the gray points are points that we have no hope of seeing for the foreseeable future. And what's cool is that the telescope that I was doing these predictions for, it's a balloon-based telescope. So what you're seeing here, this is where the instrument and the telescope and the mirror are inside. It's called the gondola. And back here in the distance, you can see the balloon that's going to lift it up above most of the atmosphere. So the cool trick you can play is you know that the atmosphere is a problem, so if instead of going to space, you can just fly a telescope above most of the atmosphere, it turns out you can do a pretty good job if you look within this 8 nanometer bandpass. So between 200 and 208 nanometers, the atmosphere is very clear to UV light. So that's the plan. So we've built a telescope that should be flying around fall 2017, so pretty soon now. I've been working on this for years, so fall 2017 feels really soon. And it's particularly exciting because it's pushing all of our UV CCDs. So the way we take pictures of UV light, this telescope is a test bed for the new, potentially, thinking far in the future, the next space telescope that we might want to build to replace Hubble. We'll probably be using technology that's been demoed by telescopes like this that we fly. Okay, so just to summarize, most of the mass of galaxies is found beyond their stellar disks, I hope you've convinced you of, and that the outskirts of these galaxies are actually really important and really interesting. The properties of this gas are hard to observe, but we're making progress. We have actual observations that are connected to galaxies now that we understand. More work is needed to explain the observed properties of this gas. So again, the simulations don't predict this at all, and so what's actually happening out there is kind of a mystery. And understanding this gas is fundamental to understanding the evolution of galaxies in general. So when we talk about galaxies, we have to also be including this gas that's feeding them and that's being destroyed by them. So, thank you. Do you have any questions? Okay, yeah. I'm sorry, back to that.
I think gas is equivalent to plasma, is what I learned in high school. Is that, or is there a distinction?
No, so yeah, I think plasma is normally something that's considered ionized, but this gas is also ionized for the most part, yeah, so other than the neutral hydrogen, which I mentioned.
So where are all the electrons?
They're out there. They'll also give off light. But what's interesting about these specific ions is that they give off signatures that are easy to detect. So the oxygen 6 is a very specific transfer. So electrons, as they move around in atoms, give off light at very specific wavelengths. And when you see oxygen 6, you know that you're seeing that process that's generating it, and so you can associate it with the temperature, for example. And so looking in these kind of ions, is useful in terms of being also a diagnostic tool.
You show the diameter of the outer disk, and then you show the spider web of this galaxy connected up close to this galaxy.
Yeah.
Can you help me with the relative size? That disk that you showed versus the distance between one dot on that spider web plot and the next one.
So that spider web plot is pretty zoomed out, so it's going to be, the disk is on scales of hundreds of kiloparsecs, so the distances are going to be like tens, hundreds of megaparsecs for like the very big web. But there are obviously big galaxies closer together, like the Milky Way and Andromeda. That's just a particularly zoomed out picture.
In the real universe, the average size of a void is like 40 megaparsecs across, 60 megaparsecs across inside. So when you see the web, the empty holes, they're,
Mostly empty hole.
yeah, well, that's a spider web is mostly emptiness. A little bit of string, right?
But then the galaxies are mostly in the parts that are overdense. So it's a...
Comparing galaxies, how homogeneous are the mixes?
I'm sorry, the what?
When you compare one group of galaxies to another,
Yeah.
how similar are they in terms of the chemical composition of the gases?
Lauren, can you repeat that for the online audience?
Oh, sure, sorry. So the question is, when you're looking at different populations, how similar are the chemical mixtures between them? So we expect the stars to be giving off the same kinds of metals, regardless of the kind of galaxy it is. But how far they're going to go is going to vary a lot depending on the mass of the galaxy. So a massive galaxy, like the Milky Way, for example, is going to generate a lot of supernovas, it's going to go off a lot of energy, but they're also really massive, so they can hold on to things more strongly. Okay. Thanks. I know that's going to be bad. Right. So we expect the relative mixtures to be the same, or at least what's generated to be the same, but how far that gas is going to extend, and this is a complicated question. How far that gas is going to extend and what gas is flowing in is going to be very different depending on the mass of the galaxy. So these properties that we're seeing, say here in the data, are going to be very different depending on what mass galaxy you're looking at. Does that answer your question? I hope.
Questions here?
Yes, Fireball 2, you were saying, is that a NASA-based telescope?
It's being built between Columbia, JPL, Caltech, and an institute in France. So it's a collaboration mostly between NASA and the French version.
So when they go up and they get all this data, do those institutes have that data, or is that sort of public? And is there a mad scramble to use that data to then publish?
That's a good question. I'm
So the
looking.
question is, who owns the data at the after an instrument like that is flown? Who owns the data? Does it ever become public?
So I'm not sure if there's the same way as Hubble where you have to make it public, for example, because it's operating on a much smaller scale. So I know, I think there's also a time frame in which is probably proprietary. So you'll have access to it first for a long time to be able to publish the data since you led the mission, and then it becomes public. Ideally, you're going to want to share the data with everyone anyway. So presumably it's going to be public, but we're also going to try and publish the results that we set out to do first, and then anyone else can do what they want with it. So, and you want that turnaround to be as fast as possible. So, yeah.
In measuring the absorption of the light from the quasar by the gas, don't you need to know a lot about the nature of the quasar without the galaxy in the way?
Yeah.
How do you?
The question is, you're using a quasar and you're absorbing the light from the quasar, so you really need to know what a quasar looks like first, right?
That's right, yeah. So there's a few things that go into that. So first, so I don't do the observations, but at first, they do understand what the quasar is supposed to look like. And again, part of that's going to come from the fact that these dips that you're seeing are particularly obvious. So you wouldn't expect naturally for a quasar, if it's emitting light, to have huge, broad absorption features like that. Maybe I can go back to the plot in the beginning.
Are all quasars alike in terms of the nature of the light that they're?
Yeah, so there's some variety. There's different types of quasars, but they do fall into categories, and so you can identify this is this type of quasar and this is that type of quasar. So you can subtract it. Sorry. There you go. And again, so the other thing that comes into this is what's useful is we do know that there are galaxies there, and we know what redshift they're at. And so we can identify, when you see this absorption, because you know that the galaxy is there, you can also identify that with the galaxy. So you're saying, I see this feature, I'm expecting this feature, so it is this feature. So you have this extra information that this is supposed to be there, we think.
I mean, just if I may just throw one other thing, is that you know the redshift of the galaxy, right? So the absorption lines are going to be similarly redshifted, and you've got like 0.1662 for the redshift.
Yeah.
So if that didn't occur for the carbon line redshifted by that much, it wouldn't fit, but it does.
Right. Yeah. So it wouldn't be identified as being associated with that galaxy. Yeah.
Okay. Other questions?
You talked to us about quasars, but I've also heard of pulsars. Are they like a type of quasar, or are they different?
Thank you. I'm joking.
Repeat the question.
So the question is, what's the difference between a quasar and a pulsar?
In my head. Yes.
Yes. So quasars are black holes that are accreting material that then give off large amounts of light. Pulsars are neutron stars that are rotating, and so you see the emission that they're giving off as they rotate around. So they're different. So they're not going to be these bright sources that we can use to observe galaxies like that. Pulsars are happening within a galaxy that we can see. Yeah, they're not going to be these distant objects.
Question?
Yeah, and add to that, my understanding, the quasars are usually from supermassive black holes?
Yes, that's right.
Quasars.
At the center of the galaxy?
Yes.
Repeating the question, quasars are from supermassive black holes, and she said?
Yes. Yeah, that's okay, that's so right.
I'm trying to be careful because the last couple of months, I've always gotten one comment saying, "Oh, please repeat the question for the online audience."
I was literally here this morning, we were doing the same thing, and I made a mental note of repeat the question, and then you're in the moment.
And
you
it's
totally
so
forget.
hard to do.
So
Yeah, all
thank
the
you.
way in the back there.
Are we looking at these galaxies that are similar to the Milky Way because it's easier to see features about a distant galaxy than it is to see features about our own, and we're trying to figure out the structure of our own?
Yeah, that's right. So the question is, is there a reason we're looking at galaxies like the Milky Way that are a bit further away as opposed to just looking at the Milky Way itself? The answer is, it's very hard to get this kind of picture of the Milky Way because we're inside of it. So there are people who are studying the CGM of the Milky Way, but a large portion of how you're doing this is these background sources, and then they're easy to identify because the galaxies have this redshift where you can see this absorption associated with it. With the Milky Way, it's so nearby that the gas is all sort of moving at the same velocity, and so being able to identify these kinds of features is difficult.
I would think every quasar we know is going to have absorption lines in our own galaxy.
Yeah, that's right. But like, yeah, it's.
Or our galaxy will show absorption lines from every quasar we see, rather.
But yeah, but I guess also just getting a census of what gas is there, it's difficult, yeah. Let me think about that a little more, give me a second, and then I'll have a better answer maybe after this, yeah.
Well, the cloud that's around our own Milky Way will be relatively continuous on the near end, on the low redshift end.
Yeah.
And when you have these higher redshift objects, you can see the specific lines associated with that redshift. And what I was going to say is that, what excites me about this is also seeing how the gas distribution changes with redshift. Because as you're going out in redshift, you're also changing time, and you can see a bit about how galaxies develop over time using this, instead of just trying to see only the bright cores of galaxies, which really biases us, especially at larger redshift, to only the bright spots of the galaxy. Being able to get this low density stuff really gives us a better picture of the overall structure of galaxies across redshift. One of my favorite things about it.
Yeah.
Hey Frank, going back to the red dwarf and the southern planets, at only 40 light years, if there was technology advanced on one of those planets, we should definitely have been hearing from them by now.
The question is, since it's only 40 light years away, and if they have advanced technology, say radio antennas, right, and they were beaming towards us, we've had radio antennas for over 40 years, so we should be getting signals from them if there are signals being sent. Yeah, maybe. As I said, we don't know how old these planets are. Have they been around? I mean, it took 4 billion years for intelligent life to develop, or supposedly intelligent life to develop. And so if these planets are only a billion years old, maybe life hasn't developed there. But yeah, no, it is definitely a place that the SETI project will look.
One of the things that's hard too is it's hard to generate a beam that stays coherent enough over those kinds of distances as well. So like if they were trying to send us something, it's hard, at least for us, to send something like that far. So maybe it's also hard for them, or maybe they're a lot smarter and we're going to find them now, who knows.
But if we wanted to have a conversation, it would take less than a century to be able to have a conversation back and forth. So that's good. That's really good on astronomical terms. We had another question there.
The volume of gas around the disk, does that affect the light coming from the disk by absorption?
So the question is, you've got all this gas around the disk, how much does that affect the light coming from the disk? How much is absorbed? Is it significant?
So there will be some of the light will be blocked since it's going through this gas, but it's so diffuse compared to the gas that's going to be in the disk itself that's what's going to be doing most of the blocking of the light, not necessarily this gas.
You get some distortion of the spectrum?
I mean, maybe if we were looking at much higher resolution than this, but but we're not going to be able to see something like that here.
So what are the density range of this, what's the density range of these, this low density gas outside it versus, say, the density of a giant molecular cloud type thing? I mean, 'cause we have such a huge range of densities in astronomy. It's hard to get your mind around that.
That exact is hard for me, but so in the diffuse volume, the densities are going to be something closer to say 10 to the negative 4 centimeters per centimeters cubed, 10 to the negative 5. In the disk, we talk about things that are closer to 1. So it's a factor of 10,000, 100,000 difference, and so this absorption from the disk as it's traveling through is going to be a lot greater than from this gas that's in the outskirts.
Okay, good. Any other questions? All right, we will meet back here next month for integrated field unit spectroscopy. Do not be afraid, it's a great topic.